Hello everybody, today I'll be helping you understand the thermal properties of matter. By this video, you'll understand how the thermal properties of matter is there in all different forms of matter. Understanding these properties is very important because this will set a base to your thermal physics and in general physics as well. It will also help you understand the basics of engineering and how things work in our daily lives. You may ask how in our daily lives? So let me set an example. Suppose I kept a really delicious meal on the table. Could you explain why the smell spreads throughout the room? It's difficult to state so because we do not know the basics of thermal properties of matter. These small things in our daily lives are related to properties of matter, not just in thermal sense but in general sense. Without any further ado, let's begin. If I say heat, you may think of temperature and heat being the same thing. But let me say this clear, they both aren't. Temperature measures the average kinetic energy of molecules within a substance. Basically, in simple words, temperature tells how cold or hot an object is. Whereas, on the other hand, heat is a form of energy transferred due to temperature difference and usually measured in joules. So, if I say this, the temperature and heat are different things, now would you agree? The absolute zero, or if we say 0 Kelvin, represents the minimum heat capacity and specific heat. Specific heat capacity is basically the heat needed to raise the temperature of 1 kg of a substance by 1 Celsius. Or in other words, to make an object be warm or hot by a specific temperature. High specific heat capacities indicates that the object or substance is excellent for heat storage and regulation. Good conductors of heat capacities are usually used in cooking and heat sinks. If a substance, for example glass, has lower specific heat capacity, it will heat up and cool down quickly, which is not preferred while cooking. That's why we use good conductors. Specific heat capacity is represented with a small c. High heat capacity indicates that the substance will heat slowly, and low heat capacity indicates that the substance will heat quickly. The formula for the same is Q equals to mc delta T. In this equation, Q represents heat in joules, m represents mass in kg, C represents specific heat capacity in joule per kg degree Celsius. Delta T represents the change in temperature. Don't get confused in change in temperature and time. Usually, time is given in the question to confuse you. There are various uses of specific heat capacity. Some of them are water is used in hot water bottles or car radiators because they have high heat capacity, whereas metal pans are used because they heat quickly, indicating they have low heat capacity, with a rubber handle so that our hand doesn't get burned. We have learned earlier that change in temperature or pressure helps in phase changes from one state to another. Changes in phases include melting, boiling, sublimation, condensation, evaporation. These transitions are represented on the phase diagram. Latent energy is the heat required to change state without changing its temperature. Its equation is Q equals to m times L. In it, Q represents heat, m equals to mass, and L equals to latent energy. Latent heat of vaporization is liquid to solid or solid to liquid, whereas latent heat of fusion is solid to liquid, liquid to gas. Before we start with conduction, convection radiation, or in other terms, thermal energy transfers, I would like to say few applications of expansion and causes of the same. Materials expand when heated due to increased kinetic energy or vibration. This phenomena is known as thermal expansion. There are three thermal expansions: linear expansion, area expansion, volumetric expansion. Linear expansion refers to when the length increases, basically in solids. And area expansions refers when the surface area increases. Volumetric expansion refers to when the volume increases, usually in liquid and gases. There are few formulas for the same. For linear expansion, it can be calculated by the delta L, known as change in length, which will equals to A times L delta T. In this equation, A is the coefficient of the linear expansion, L is the original length, and delta T is the temperature change. Applications of thermal expansions. They are used in thermometers, bimetallic strips, and railway tracks. Now let's come to thermal energy transfers. First, we have conduction. Conduction is the process of heat transfer through direct contact between particles, usually occurred in solids. Transfer of heat energy through solids without movement of material itself is conduction in simpler words. Particles vibrate faster when heated and passes on energy to neighboring particles. Metals are good conductors or good materials for conduction. Why are metals good conductors, you may ask? They have free electrons that carry energy quietly and also through the material. Poor conductors of thermal energy or poor metals for conduction is known as insulators. Wood, plastic, glass, air do not have free electrons, therefore making them poor conductors for conduction. It is used to prevent heat transfer. It is usually influenced by Fourier's law, where Q representing the heat equals to K times A bracket delta T upon D bracket close times T. K represents the thermal conductivity, and others I have told in almost all the formulas before in the video. Now let's come to convection. Convection is the heat transferred by fluid motions. This can be natural or forced. But let me tell you convection in a simpler form. Transfer of heat in liquids and gases by movement of particles. If you want to write a definition for the same, you can write the second one because it's simpler and would be easier to be remembered. Process of convection. When a fluid, which is liquid or gas, is heated, the particles gain energy, which makes them to move faster and becomes less dense. The warmer and less dense fluid rises. The cooler and more denser fluid sinks to take its place. This creates a convection current. Examples for the same are boiling water in a pot, warm air rising from a beaker, sea breeze during the day, and various others. If somebody asks you the applications for convection, it would be hot air balloons and room heaters placed near the floor, because the heat rises in both the cases. Let's come to the third and the last way of thermal energy transfer, which is radiation. Heat transfer through electrowaves is known as radiation. It can occur in a vacuum space too. In simpler words, radiation is the transfer of heat through electromagnetic waves, which is also known as infrared waves. It does not need a medium, unlike convection and conduction. It can travel through vacuum, as I mentioned before. Factors affecting radiation is the color of the surface or the material. For example, dull black surface is the most radiation emitter, in which radiation is absorbed, making it a good conductor. Whereas white shiny surfaces are poor absorbers and emitters. For its application or examples, there are sun's heat reaching the earth, solar panels absorb infrared radiation, thermal flask with shiny inner surface to reduce radiation. Let me help you understand the applications in daily life of radiation in more detail. Flasks are usually made in vacuum because it stops conduction and convection. Insulated stoppers are also made for the same. Clothing. If you wear dark clothes in winter, it absorbs the heat, whereas light clothes in summer reflects the heat. With that, our thermal energy transfers is finished. Let me summarize and conclude today's video. We have covered essential thermal properties such as temperature, heat capacity, phase changes, heat transfer, and thermal expansion. These principles are really important to set a base for your physics, or in other words, thermal physics. I hope this video helped you all. This was a rapid revision video for you all, which it can help you during your exam times. Thank you. Keep learning science.